Okay, so this is our curve that we've gained from stretching and elastic band. And once again, we've got a different loading curve to an unloading curve. We can see that immediately we're not following Hooke's law. The extension is never proportional to the applied force. I've realised that when I exported this, I didn't have the axes, so I've got my force in newtons, and I've got my extension in meters. But the logic of what we're dealing with is still the same. So we still have a difference in the area under the two graphs, and that area is going to represent a work. Now, what you'll notice is that my elastic band hasn't exactly gone in all the way back down to its original length. There's a slight reason for that I'll describe it later. But often you'd find that it would. But what is this sort of energy? It's not gone into, what it has not done is work that's been done in permanently deforming the rubber. This is energy that if you stretch a rubber band and you keep stretching it and like relaxing it and keep going round, 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 what you'll find is that rubber bands, like a hairband or anything, will get warm. So in stretching and unloading a rubber band, what happens is that you lose, the rubber band will get warmer, so it gains this work as heat. So it's not in a permanent deformation of the structure of the material, it's actually in being a bit warmer. So in this case, what we have is the area between the loading and unloading lines is the energy gained by the band as heat. So during repeated cycles, so if you stretch and relax, stretch and relax an elastic band, it will get hotter and hotter and hotter over successive cycles. Oh, that was upsetting. Didn't mean to do that. So let's try again. So that is essentially just the way in which we deal with a rubber band, and it's the same sort of idea, same sort of stuff. So I thought it might be interesting to kind of describe a little bit about what this graph is and the behavior, the difference in the behavior between metals and pieces of elastic. So this exhibits elastic behavior. So let's think about the actual structure. So this is bits that you don't need to know for the A level. They'll never go into this level of detail, but it's interesting enough to have a difference of the. So I'm going to draw a line under this. So I'm going to do metals versus rubber as a kind of a diagram sort of change. So metals, if you think about metallic bonding, what you've got a series of particles that are bonded and they form a nice regular pattern. And in terms of physics, what we can do is often when we apply a force at either end, what we do is we actually stretch apart the particles themselves. And one of the ways in which we can model, the actual things between particles, we model each particle as almost like having a little spring between them. And so we can stretch them, and they all stretch because they've all got little springs between them. So they're just like little particles connected by tiny little springs is kind of how we model it. And what we do is we stretch them apart and apart and apart. The thing is, eventually what you'll get is to a point where if you stretch these things, like say to where they're stretched out like this, obviously we've got a bit longer, but eventually it will hit. This is the way I was thinking about it. Eventually you'll hit a point where the spaces between sort of the spaces apart as you pull these things apart, as you increase the force. Well, these springs are no longer good enough to hold together. And what you'll notice is that you actually hit a point where the space is big enough for this particle to slot into there. It fits nicely into there. And this particle fits nicely into there. And this particle into there. And so on and so forth. And so what you end up with is something which has become permanently deformed, because now what you've got is a series of things, I didn't quite fit into that one, but you've now got a longer wire, and they can just start forming the springs in, which is why we then saw that it still had a springy quality when we were allowing the metal springs to end. But when you remove the force, well, these particles are not going to pop back out when you just suddenly remove the force. They're not going to say, oh yeah, no, I was previously over there. They're like two lines to become one line. That line is now physically longer. So you reach a point where, by deforming it, you've essentially made a longer line. So, where the atoms have slipped together. And atoms, in different rows, can move across each other, and it's called dislocations and things like that. So metals, this is one of the reasons why they behave elastically up to a point when these things will slip in, and then you end up with just a longer wire or a longer spring. So that's how we can kind of think about the atomic structure of how the atoms in a metal wire or spring behave. What about rubber? Well, rubber is a polymer. And polymers are kind of arranged in a sort of a random, haphazard pattern. And the thing is, so they're a bit like shoelaces that are kind of tied over together. And what there are is, as you apply a force to them, what you've got are two forms of bonds going on. You've got the bonds that hold different chains together, and these bonds are fairly weak. Okay, so they're not very strong, but they're just holding these different chains together. And if we look at the shape of our curve, at the start there's a bit of resistance, and then this fact that it curves out suddenly means that what happens is it becomes very easy to stretch the rubber band. And what is happening there is that these little bonds are being broken, and we end up with a situation where we apply a bit of force, and we end up with a situation where our little strips are able just to sort of become more straight. So we stop them being tied up so much, they become a bit more straight, and so it becomes quite easy. So it's sort of easy to sort them out. And we get a big extension for little force. Okay, and the reason we get a big extension for little force is because we break the little weak, colourful bonds, and then we stretch it quite a lot. But then what happens here? It goes suddenly very, very, very sharply up, and we kind of hit a maximum point. And the reason we have that is that we end up reaching a point where our polymers are essentially straight lines. And now we have a very different problem, because we're trying to apply forces to extend outwards. But now we're dealing with the forces that are holding this polymer together, inside the polymer. Those bonds are very, very, very strong. They do not have the same give as, say, a metal as we're dealing with in the spring. So here, these forces are very strong. So now this material becomes very stiff. Okay, and it becomes very hard to get any more extension. And essentially, what will happen is that there'll be very, very, very little change in the length of the rubber. It'll eventually just break. And so that's sort of the different different kind of properties between metals, which we have to deal with and think about the atoms themselves, and polymers, rubber, where we think about long, huge chains and molecules that are unwound. Now, one of the things that's also interesting, however, is that this ends up being a bit longer when you let it go. So when you remove the force, it remains a little bit extended. Ooh. Now, that's definitely not what I wanted to do. One of the things that's quite weird about that is that stretched rubber is rubber which is held like this. And this is a very ordered state. This is exceptionally ordered. This is not where you would normally have things to do, but it's very finely balanced. It's kind of unstable. If you have this sort of, this is how rubber would normally exist, but we've put it, by stressing it, we've put it into this state here. And when we unload it, we end up slightly with a higher load. One of the most amazing things is that by putting a little heat in, by adding it a little bit, we will make those chains sort of kink up. And in kinking up, what they'll do is then they will start crossing each other again, and you start reforming these bonds. So what will happen is that if you stretch up rubber and it ends up being a bit longer, if you heat it up, it'll then ping back to its original shape. Or original sort of length. That's kind of the way in which rubber works. Kind of an interesting weirdness about that. Now, this kind of curve that rubber is quite famous for, it's got a fancy name. It's called a hysteresis curve. And hysteresis basically is something where the outcome is lagging the effect. So in this case, when we come back down, we've removed forces, but we haven't shortened the thing. And this happens in a bit of magnetism. It happens in various loading and unloading curves. But the difference between the two is called a hysteresis loop. The metal hysteresis loop, which again you've seen, much generally, although it's hard to see unless they're on the same thing, it's much smaller as an impact. So yeah, these are, and we can design bits of rubber with either very long or very short hysteresis loops, depending on what we want them to do. And we can change the properties, adding stuff. So and by doing that, what you do is you sort of throw in some impurities. So you might throw in stuff that allows the rubber to sort of like tighten up around. So you might throw in some impurities. It's a bit like, if you remember chemistry and alloying, it's the same thing. But it's got a fancy name. It's called vulcanization. You can vulcanize rubber, and therefore you can change its properties to make it stretch not quite so much. Pure rubber stretches a huge amount. So yeah, so that's how rubber kind of behaves, and that's just a little bit of extra info on the differences between rubber and metals and why we get slightly different shapes of curves. Next one.